All right, thank you. Thanks a lot to the organizers for the invitation to give this talk. My name is Heather Logan, and I'm a professor of theoretical particle physics at Carleton University in Ottawa. And I'm going to talk about some work that I did with my former PhD student who graduated a couple of years ago now. But most of the work was done actually after he graduated and left to do a postdoc at Triumph in Vancouver. And the topic that I wanted to talk about today is sort of broadly speaking, symmetries and renormalization. And more specifically, I'm going to say some things about CP violation, which is violation of what was for a long time thought to be one of the fundamental symmetries of physics, and some details of how that shows up in theories beyond the standard model. On the first slide, I put the archive numbers of our papers in case you're interested, or you can like search on my name in Inspire or whatever. Okay, so here's the outline of what I'm going to talk about. I'm going to give an extended introduction to CP, the symmetry that I mentioned, and CP violation, and what we know experimentally in terms of that, and how that is described within the standard model of particle physics. And then I will introduce an extension. So I mostly work on Higgs physics, so physics of electroweak symmetry breaking. I'm going to introduce one of the simplest extensions of the standard model Higgs sector, which is known as the two Higgs doublet model. Then I'm going to go on a little bit of a excursion into discussing radiative corrections and renormalizability and some of the principles behind that. I'm mostly going to talk then about CP violation in the two Higgs doublet model and how that sort of seeps in from the known CP violation within the standard model. I'll have one slide on practical consequences. The question mark should maybe tell you something here. And then I'll conclude. And at the very end, I have a single slide on a resource that I've produced for some inclusion related things. Okay, so what is CP? CP is a combination of two symmetries. The phi stands for charge conjugation. That's like on the next couple of slides. The P stands for parity. So let me talk about parity first. So parity, the parity operation, you may have seen this in like third year quantum mechanics. The parity operation is the inversion of the coordinate system. So basically taking the position vector, r vector, and just flipping the sign of x, y, and z, right? So you invert the coordinate system. That has the effect of taking all momenta to minus the momenta, right? Now, angular momentum is interesting. It's what's known as an axial vector because it's r cross p. And so if you take r to minus r and p to minus p, you actually get L stays the same under this parity operation. And so if you take L and dot it into something like p, the momentum, you get a scalar which changes sign under parity. And this combination is known as helicity, and this will come up a little later as well, right? So up until the mid-1950s, parity was believed to be preserved in all physical processes. So in gravitational processes, in electromagnetic processes, in the strong interactions. So if you've done quantum mechanics and you've seen like the hydrogen atom, you can characterize the wave functions of the hydrogen atom, the energy eigenstates, by their transformation property under parity. And some of them are odd parity and some of them are even parity, meaning they go to either plus themselves or minus themselves under a parity inversion. And so it was believed that this was a good symmetry of nature, right? But it had not actually been experimentally checked in processes involving the weak interactions yet at that time. And this sort of gap was flagged by T.D. Lee and Xian Yang, who I believe were working at Princeton. I might get this wrong, either Princeton or I think actually Columbia University. Sorry, I should have looked this up before. This picture is from the University of Chicago Photographic Archive, but I think that they were not actually at University of Chicago, right? And they basically noticed, all right, like people have checked this in gravitational, electromagnetic, and strong interactions, but not yet in weak interactions. So someone should do the experiment, basically is what they said. And someone did the experiment. Within a couple of months, Chen Wu, who was at the same, I suspect it must have been Columbia because she was at the same institution as them. And within a few months, so just, the calendar switched over to 1957, she did the experimental test, basically looking at beta decay of cobalt-60 nuclei. So cobalt-60 is an unstable nuclear isotope. The nucleus has a spin. You can spin polarize the nuclei. And then basically the experiment was to look at what direction the beta, the electron, comes out, and then look at what direction the nuclear de-excitation gamma comes out, and look at the correlations between those two. Because the de-excitation, if parity is violated, one of them, like, it will not be symmetric, basically. Okay. So she did this experiment, discovered that parity was indeed violated in the weak interactions. And in fact, we know now that parity is maximally violated in the weak interactions. Like, it's as violated as it could possibly be. This observation of this discovery of parity violation in the weak interactions also explained another mystery that was floating around at the time, which was how the weak interaction decays of charged kaons. So a kaon is a meson, it's a quark-antiquark bound state. And the charged kaon, K plus, is a strange antiquark and an up quark, right? Bound state is net charge plus, okay? And it had been observed that there were these particles, some positively charged particles you can produce by shooting protons into a target and then gathering up the crud that comes off, right? Some positively charged particles. Some of them decay into 2 pions. Some of them decay into 3 pions. At that time, because it was thought that parity was preserved, right, in everything, those were classified as 2 separate particles, but they had the same lifetime and the same mass. And that's really weird if it's really 2 different particles. So how can these decays coexist? To explain why this was seen as so weird, I want to take a foray into quantum mechanics, right? So in quantum mechanics, if you have a quantity that can be described by an operator that then acts on a wave function and gives you a number which tells you what that quantity is for that wave function, okay? If you have a quantity that's conserved, that implies that its operator, this O, commutes with the Hamiltonian. And the way you can see that is that if you have a quantity which is conserved, this operator times a wave function, the operator, it shouldn't depend, the operator itself should have no time dependence. The eigenvalue of the operator shouldn't change with time, right? That's what it means to be conserved. But d by dt is basically the operator, which is the Hamiltonian. So the Hamiltonian is p squared over 2m, the kinetic energy part, plus v, the potential energy part. It's that thing that you put on the left-hand side of Schrodinger's equation, and then you have equals IH bar d by dt psi on the right-hand side, right? So that's the Hamiltonian, is the left, the kinetic plus potential energy piece, right? Now, if some operator commutes with the Hamiltonian, that implies that eigenstates of the Hamiltonian can also be chosen in a basis that are eigenstates of O as well, right? And this comes up in quantum mechanics when you're doing like degenerate perturbation theory, or you're doing like the Stark effect or fine structure and stuff like that, right? You classify the energy eigenstates as in terms of their transformation properties under some other symmetry, and then you can like do perturbation theory on those guys, right? And so, yeah, so that is basically, it means that the Hamiltonian and whatever operator have to have a simultaneous eigenbasis. Now, in quantum field theory, what that implies is that any mass eigenstate that's a single particle and not like 2 particles that happen to have the same exact mass, right? So non-degenerate. Any mass eigenstates, because the energy eigenstates in quantum field theory are mass eigenstates, okay? Any mass eigenstate must also be an eigenstate of all conserved symmetries, right? K plus is a mass eigenstate, but it's not an eigenstate of parity. And therefore, parity must not be conserved, because if parity were conserved, you'd be able to write K plus as an eigenstate of parity as well, okay? Right, and that resolves the puzzle because it tells you, oh, there's just 1 particle. It's just that parity is not conserved. So some of the time it decays into 2 pions and some of the time it decays into 3 pions, right? Okay, so that's parity. That's the P part of CP. Now I want to talk about charge conjugation. So that's the C, right? So charge conjugation, the charge conjugation operation swaps each particle for its antiparticle. And it turns out that weak interactions, at least like with single interaction of the weak interactions, conserves the combined operation of charge conjugation and parity. So basically, to do this, you exchange each particle for its antiparticle and also flip all the helicities. So if you have a neutrino, a left-handed neutrino, and you do parity on it, you'd get a right-handed neutrino, but those don't exist as far as we know. So at least they have never been experimentally observed, right? If you have a left-handed neutrino and you do charge conjugation, you get a left-handed antineutrino. Those have also never been observed, right? But if you have a left-handed neutrino and you do C and P, so you flip it to being parity, to being right-handed, and you flip the charge conjugation to be now an antineutrino, these are basically the antiparticles of left-handed neutrinos. I mean, they're the CP conjugates of left-handed neutrinos, but these exist, right? These are the antineutrinos that come out in beta decay, for example, when you do beta decay, right? The right-handed antineutrinos. Now, I said the combined operation is conserved. It was believed to be true for an entire 7 years after the discovery of parity violation, until CP was also experimentally demonstrated to be slightly, only slightly, violated in weak interaction processes. So now we're in the mid-1960s. CP violation, again, was discovered in the kaon system. So kaons are really cool. And it was discovered at the alternating gradient synchrotron at Brookhaven National Lab in New York. So the AGS alternating gradient synchrotron is this ring here, okay? This picture is from like now, or a few years ago, and a larger accelerator was built in the meantime, but using the old AGS as a booster. So in the 1960s, this was like the hot current accelerator. And one thing they were doing is accelerating protons, shooting them into a target. Crud comes out the back, basically hadronic junk, right, from the proton collisions on other atomic nuclei. And amongst that stuff are mesons, including kaons, right? And some of those mesons are neutral kaons. So I talked about charged kaons before. The neutral kaons are basically a strange quark and a down antiquark, or an anti-strange quark and a down quark, right? So things that are net electrically neutral and having one antiquark and one quark, right? And of the neutral kaons, there's two of them. They can be classified, and I'll explain a little more about this on the next slide, classified as K short, which decays to 2 pions, and is CP even. So a single pion is CP odd, the 2 pion system is CP even, okay? It's called K short because it has a relatively short decay length, only about 3 centimeters. C tau is the lifetime, right? The time constant in the exponential decay. C tau translates that into a length, right? So you can kind of get a sense of how far they're going to travel if you take into account how fast they're moving in time dilation, right? And so that tells you that the decay length, the distance they'll travel before decaying, is about 3 centimeters. So very close to the target they'll have decayed or started, exponentially decaying. K long, which decays into 3 pions and is CP odd, its C tau is like 15 meters. So basically it's gone way the heck down onto the other side of the lab. And by the time you're over there, basically all of your K shorts have decayed away and you just have a pure sample of K long, right? That's important because it turned out, and what was discovered in 1964, is that the K long also decays to 2 pions, the CP even final state, okay? But very rarely, only 0.3% of the time, right? And so this is telling, this was interpreted based on this idea that you have an eigenstate of the Hamiltonian, it's a mass eigenstate, but it's not an eigenstate of CP because it sometimes decays to a CP even final state. And that implies that CP is also violated, right? So this violation of CP is explained in the standard model by the 3-generation Kabibo, Kobayashi, Maskawa quark mixing matrix, right? So what this matrix is, it's a 3x3 unitary matrix, okay? The elements of it control the relative strengths of the weak interactions between the 3 positively charged quarks, okay, and the 3 negatively charged quarks, right? So if I have a charm quark and it's going to either decay to a strange quark or to a down quark, the relative strengths of these are controlled by two of the elements of this matrix, right? It's a unitary matrix, but you can absorb some of the phases in the unitary matrix into unphysical field redefinitions of the quarks. And if you do that, you can absorb everything except three angles, which are basically like the Euler angles for a 3D rotation matrix, together with one complex phase into these unphysical redefinitions. So there's 3 + 1 physical parameters in this quark mixing matrix. And this complex phase is the source for all of the CP violation that has been experimentally, like definitively observed up till now, okay? I say definitively because there are hints of CP violation in experiments doing neutrino oscillations, but they're not quite like at the 5 sigma level, right? For being able to say this is definitively there, okay? And this paradigm of the CP violation here was well established at the so-called B factories, Babar and Bell, during the 20-aughts, okay? So how does this work? So the neutral kaon system, I said there's a K0, which is anti-strange and down, and a K0 bar, it's anti-particle, which is anti-down and strange, okay? And these two can transform into each other due to the weak interactions. So basically, exchanging a W boson turns, say, the down quark into either an up quark, a charred quark, or a top quark, okay? And then you do another W boson to make this be the anti-strange quark. And then you can do the same thing over here, and you get, basically, you can swap a D into an S, right? And an S bar into a D bar. And that turns your kaon into a K0 bar, right? Into its own antiparticle. And what this does in terms of the quantum mechanics is it gives you off-diagonal elements to the mass squared matrix. So basically, if your couplings of the W to these quarks were all real, right? So if this complex phase were 0, what you get is a mass squared matrix that looks like this. On the diagonal are the masses of these two kaons, which are equal to each other because they're antiparticles of each other. And on the off diagonal, there's this tiny number, which is very small compared to m squared, which is basically what you get if you calculate this process, right? The mixing process here. And this matrix is real, right? Now, a 2x2 real matrix, you can calculate the eigenvalues, okay? When you have a matrix for which the diagonal elements are the same, adding some off-diagonal thing basically gives you a 45-degree rotation to the eigenvectors. So the eigenvectors of this are 1, 1, and 1, - 1 with an appropriate normalization, right? And the eigenvalues are basically this thing plus epsilon or this thing minus epsilon, okay? So the eigenvectors, I said it's 1, 1 or 1 - 1, okay? The kaon being a meson transforms or would transform under CP into minus. So this K0 transforms into minus K0 bar under CP. And so this whole combination goes to minus K0 bar plus K0 over root 2, which is just minus the original thing. So that's odd under CP, okay? And so this we expect is going to decay to 3 pions, and we would identify that as the K log. And then the orthogonal combination would be K even, CP even, decay to 2 pions, we'd identify that as K short. The reason that this guy is so much longer lived than that guy is that there's almost not enough energy available for a kaon to decay into 3 pions, but there's plenty for it to decay into just 2 pions. So that's basically the explanation for the difference in the lifetime, okay? So these would be CP eigenstates, and there'd be no CP violation. But what happens with this phase in the quark mixing matrix is that the off-diagonal element has a little phase in it, and e to the I theta attached to that epsilon, okay? And for the kaon system, it turns out that theta is quite small, right? Now, if you calculate this diagram and then you calculate the diagram going the other direction, the phase is opposite, which you can kind of also see because this matrix has to be Hermitian in order for its eigenvalues to be real, which you want for masses, so they need to be real, okay? The eigenvalues are unchanged by putting this phase here, but the eigenvectors are changed. And the way they're changed is there's a phase that gets attached to one of the entries in the eigenvalue, just the same phase here, right? Now, if you put that in and then you do a little bit of math, you get basically that you can rewrite these new eigenvectors in terms of the original eigenvectors. And what you wind up with is that this phase causes a small admixture. Remember, theta is small, so sine theta is small, of the even CP eigenstate into the would-be odd CP eigenstate and vice versa, okay? So these are the true mass eigenstates K long and K short, but they're not CP eigenstates anymore. And it's due to this phase, right? So that's sort of a lightning overview of CP violation in quark mixing. I want to change gears now and introduce the two Higgs doublet model and then say some things about radiative corrections. Okay, so the two Higgs doublet model is an extension of the standard model by which you add a second doublet, okay, and it's a doublet under the SU2 weak interactions, okay, of Higgs bosons to the one that you have in the standard model. So in the standard model, you have the scalar field, which gives you the physical Higgs boson, which was discovered at the Large Hadron Collider in 2012. And then there are other degrees of freedom in this, which wind up giving the extra bits that make the W and Z boson be massive through electroweak symmetry breaking. The two Higgs doublet model, you just take this and copy paste and make a second one, okay? And the extra degrees of freedom you get from doing this show up as extra physical Higgs bosons. So you still have the one that's been discovered, and then you have some extra ones which have not been discovered. Okay, they've been searched for at like the Large Hadron Collider, and there are lower limits on their masses and stuff like that, but they haven't been discovered. Okay, now you have to do some model building. You have to restrict how the doublets interact with fermions in order to avoid messing up the CKM picture of quark mixing, which is pretty well tested. It's easy to do that by using some extra symmetries. And after you do that, you can describe the Higgs masses and interactions with the so-called Higgs potential, which is this big mess here. The reason I've written it is because I want to point out that all of these terms, so this has to be a Hermitian operator. It has to be Hermitian in terms like if you take the Hermitian conjugate, you get the same thing back, okay? And most of these terms, so like phi1 dagger, phi1, so dagger is the Hermitian conjugate, phi1 is this vector here, or this vector here, okay? This combination is by itself Hermitian already, so the coefficient has to be real in order for V to be Hermitian, and so on, okay? The things I've highlighted in red are basically the only two coefficients of terms that are not self-Hermitian. And so these coefficients can be complex. They don't have to be complex, but they can in principle be complex. And that complex phase is related to CP, would be related to CP violation, right? A new source of CP violation, a potential new source of CP violation. It turns out only the relative phase between these two winds up being physical, because you can get rid of some phases by absorbing them into field definitions. And the phase, so the imaginary part of this lambda 5, right, is constrained already by null searches for an electric dipole moment of the electron. So basically looking for electrons already have, we know very well, have a magnetic moment. If you look, do they also have an electric dipole moment? There's only an upper bound on that right now. But this effect through radiative corrections would contribute to an electric dipole moment of the electron. So that lets us constrain this experimentally, right? And this is a little fine-tuned, actually, even if the new Higgs bosons are quite heavy, of order 1 TeV, so 1,000 times the mass of the proton, or like 10 times the mass of the already discovered Higgs boson. This imaginary part of lambda 5 has to be less than like 1%, even though the real part can be order 1. So that's, the phase is a bit small, has to be a bit small, okay? And one way people deal with this is they just say, well, let's just assume it's CP conserving. The scalar potential is CP conserving. So assume that m squared 1, 2, and lambda 5 are real, and then like do phenomenology with that, right? That gets you the so-called real two Higgs doublet model. It's a very nice model. There's loads of theory studies. There's loads of experimental searches. There's like codes you can download that calculate the spectrum. The radiative corrections up to 2 loops for this whole model are all known. But an interesting question was raised about 4 years ago by this group working in Lisbon, Portugal, about whether this whole picture of the real two Higgs doublet model is actually consistent. And the argument is, we know that CP is violated in the weak interactions of quarks. That's well established experimentally. That's what I talked about in the introduction. And there's a known feature of quantum field theory that if you violate a symmetry like CP in the way it's violated in the standard model, that symmetry violation has to eventually propagate to any other parts of the theory via radiative corrections. So what do I mean by radiative corrections? Right? So basically the idea here is that if you have a quantum field theory and there's interactions in it, which is like all interesting quantum field theories, they can almost never be solved exactly, which sucks because it means that instead of doing exact solutions, and the reason you can't solve them exactly is basically because it's not a linear differential equation. It's a nonlinear differential equation, and so you can't just get like a bunch of your complete set of solutions and then do superposition of those solutions, right? So instead, what we do to deal with this is we use so-called perturbation theory. And we use this to calculate order by order in powers of the coupling strength of the interaction. So a weakly coupled theory is easier to do this with than a strongly coupled theory. And the way it works is, imagine you have an electron, that's the solid line, interacting with a photon, which is the wavy line, right? The first order is just a single interaction like this, and that's proportional to E, the charge of the electron, basically. But you can build up corrections to this, right? Like if the electron emits a photon, which then gets reabsorbed by the outgoing electron, this has 3 vertices in it, it's going to be E cubed. And then you can add another photon, that's going to be E to the 5th. And you can see there's more diagrams as you go to higher order, right, in perturbation theory. And this sum continues forever, right, to E to the infinity, okay? The only way you can actually calculate with this is basically to say, well, look, I'm going to calculate the order E and the order E cubed, and then I'm going to stop because the order E to the 5th, I can estimate how big that is, and it's small enough that I don't care, right? Or if you do care, you calculate these diagrams and then you stop, right? Because like, oh, E to the 7th is too small, I don't care, okay? That's the idea behind perturbation theory, right? And the way you calculate these, there's a well-defined procedure for calculating these illustrations, right? These so-called loop diagrams. They're computed using the so-called Feynman rules in particle physics and the sum over histories. So the sum over histories is basically like, I mean, it's like, in quantum mechanics where you integrate everything. You take all possible ways that the process can happen and you add them all up. So all possible ways that can happen means all of the different diagrams that can contribute, but then also if there's a momentum that's not fixed by the incoming and outgoing momenta of the external particles, you have to integrate over that momentum because that's all the different ways the process can happen, okay? So you integrate over this momentum that isn't fixed by the external kinematics, you sum up all the diagrams, right? The complication to this is that the momentum integrals can be divergent. And you might think, okay, that's going to be terrible because then you can't calculate anything, you just get infinity and the theory is BS, right? I'll get to that in a second. Okay, so the way the divergence shows up is this diagram here. The integral, we're working in special relativity, basically, right? So momentum, we do 4 momentum. So, your 3 spatial components of momentum and then the energy. So you have your energy momentum 4 vector. That, we're integrating over that. The photon here gives a factor with some stuff in the numerator, which I've not written, right? It gives a factor of 1 over k squared, where this k is the momentum. And these electrons give factors, each of them gives a factor like this. These are so-called propagators of these particles, okay? And if you look at the powers of k, when k is large, when k squared is large compared to m, there's d4k, 2 powers of k in the numerator, and then 6 powers in the denominator. So that's a net 1 over k to the 4th. And you can do these integrals in basically the 4-dimensional equivalent of spherical coordinates. And if you do that, you get basically d omega integral. I've put a lambda here, which is the highest value of momentum, okay, which we're going to then take to infinity, right? K cubed dk 1 over k to the 4th, right? That's a 1 over x integral. Integral of 1 over x is log of x. And so this is just going to equal log of whatever this high momentum cutoff is, which when you take it to infinity goes to infinity. So this is bad, okay? But what this is coming from is the high momentum, which corresponds via like de Broglie wavelength to short distance part of the integral. You might ask, well, the 0 end of this is also going to give a divergence, but when k squared goes to 0, these m's show up, and you actually have a convergent integral there at the low energy end, so you don't worry about that, okay? But the thing is that when you measure E to put it in this calculation, you're actually measuring the sum of all these processes already, right? You're measuring E in the lab at the in the Thomson limit of zero momentum transfer. You're not measuring it at infinitely short distance. And so in these calculations, you're sort of obligated to re-express the calculation in terms of measurable input processes, right? All the divergences are going to cancel. Well, sorry, I should say, when you re-express these calculations to get predictions in terms of measurable input processes to fix the parameters of the theory, all of the divergences wind up canceling in physical predictions, right? And this is, if in a theory that does this, that theory is called renormalizable. And the way this is organized, you organize the math by basically defining the coupling that shows up in that perturbative expansion, E0, is equal to a physical, so E0 is called the bare coupling. That's what appears in the Lagrangian. E is the so-called renormalized coupling that we measure physically. And then delta E is the extra piece that interpolates between E and E0. And this is divergent in general, but this piece is called the counter term. And when you calculate loop diagrams, this is going to cancel the divergence in the calculation of the renormalized predictions. So you can kind of shunt all the infinities off to one side. They all cancel, and then you can express your calculation for predictions in terms of the measured input quantities, right? And the finite parts of this calculation are meaningful, and they can be tested, and is really good, actually. So the electron, so-called electron d-2, so this is the anomalous magnetic moment of the electron, has been measured to super, super duper precision. To calculate that in terms of an independently measured quantity like the Rydberg constant in atomic physics, you have to do loop corrections in QED, basically these diagrams, okay? Out to, I think it's like 5 loops at this point is the state of the art. And the agreement works to a part in 10 to the 8th, which is astoundingly high precision, okay? So let me come back to the 2 Higgs doublet model. We got the real 2 Higgs doublet model by imposing CP invariance on the theory, right? And what that did is removed a degree of freedom. If I say, well, I can absorb the phase of n squared 1, 2 into like rephasing of phi 1, and that just pops back up into lambda 5. Lambda 5 has a real part and an imaginary part. If I say, I'm going to take that imaginary part and just chuck it, throw it out of the theory, I've thrown away 1 degree of freedom. Now, if there are divergent radiative corrections to the operators, this operator or this operator, that have imaginary parts in the divergence, we're in big trouble now because I've thrown away the counter term that I need to cancel those divergences, okay? And this is the big if, right? So if there are divergent radiative corrections that have imaginary parts, then you actually have to keep the imaginary part of lambda 5 in the theory. You can't throw it away. These guys did the calculation, a state-of-the-art 3-loop calculation, the order that they expected to find the influence of that phase in the quark mixing matrix. So basically, they wanted to get 4 couplings of the W boson, and in order to sort of shoehorn that into these processes, you needed 3 loops. But they found that the imaginary divergence canceled, actually, which was kind of curious. And that got us curious. So my former student, Carlos, heard a conference talk from these people about their calculation, thought it was super interesting. So we started working on it because we wanted first to understand why this cancellation would happen, because they basically found the cancellation, but they didn't really have like a symmetry reason for it. And we kind of got deeper and deeper and deeper into the problem, and wound up being able to demonstrate that, yeah, you have a cancellation of 3 loops. In fact, you have a cancellation of 4 loops, 5 loops, 6 loops, and then at 7 loops, you should have something that doesn't cancel. And so I want to basically spend the rest of the next few minutes, it won't be too long, okay, kind of briefly talking about what the ingredients were that go into this calculation of the CP violation, and a little bit about our analysis, okay? So we want to basically produce this process, right? So this is the sort of physical picture of this operator. So 2 phi 2s coming in, and then 2 phi 1s, the dagger means they're coming out, okay? And inside of this blob is going to be various loop diagrams, and we want to figure out what we need in here in order to get a divergence, which has an imaginary part, a non-zero imaginary part, okay? Now, clearly the first ingredient is we need some phase. We need a phase, right? Like we need the actual CP violation. And the place I want to get it from is the CP violation that we already know about from the quark mixing matrix, okay? So what does that take? There's a quantity known as the Yarlskog invariant after Cecilia Yarlskog, who proposed it in the 1980s, which is basically the reparametrization invariant measure of CP violation in this quark mixing matrix. And it's 4 factors of V. So the same 4 factors of V that showed up in the kaon mixing diagram, okay? Now, that's fine, okay? But it's more useful if I'm dealing with Higgs fields sort of in a more theoretical way. It's more useful to re-express this in terms of the quark couplings to the Higgs fields that are like one step back from giving rise to the quark mass matrices. So what that looks like is something like this. So basically here's quark, left-handed quark, right-handed down quark, Higgs doublet, and a matrix of couplings for the 3 generations, right? That couple the different quarks to the left-handed parts to the right-handed parts. Same thing for up-type quarks, same thing for leptons. I'm going to ignore the leptons because they're not involved in the CKM matrix, okay? And if you can define combinations of these so-called coupling matrices, right? Like this, YU dagger, this is Hermitian, YD dagger, this is also Hermitian. These combinations show up basically when you flip from left to right and then from right back to left, okay? It turns out that the minimal combination of these things that is going to yield a non-zero imaginary part involves 12 powers of Y. So it's this combination, and you can prove that this is the minimal combination basically because if you take this and complex conjugate it, that's the same as taking the Hermitian conjugate of the stuff inside the matrix. Each of these H hats is itself Hermitian. So the Hermitian conjugate of all this stuff is just to reverse the order. And then you can use the cyclic property of the trace to move stuff from the end to the beginning or from the beginning to the end, okay? And rearrange the terms and see if you can get back the original combination. If you can get back the original combination, it means that J equals J star and the imaginary part is 0, right? And it turns out that if you have the same number of powers of it here, of like, if you just had HU, HD, HU without the square and then HD squared, you can rearrange things to get back the exact same thing. And so then you don't have an imaginary part, right? It's only when you have 4 entries here and the first 2 have different powers than the second 2 that you actually can get something which is not self-Hermitian, okay? Okay, so that's fine. So let's take this and use it as instructions to draw the simplest loop diagrams that involve either J or J star. And those look like that, which looks like something that's a nightmare to calculate, but we're not going to actually calculate stuff. We're just going to analyze symmetries, right? And the idea is that if I want to get a 4-quark operator like this, I take all the extra legs and just like connect them together in pairs. And that makes more loops, but it gets, that it sort of shoves them inside that blob, okay? Now, the issue here is that I've set it up so that the quarks only couple to phi 2 to keep things the most similar to the standard model. There's another version of this model where these quarks would couple to phi 1 and those up quarks would couple to phi 2. We do that in our paper. I'm not going to talk about it here because it takes too long, okay? But as this is, these are all phi 2s, but what we want is 2 incoming phi 2s and 2 outgoing phi 1s. So we have to convert 2 of the outgoing phi 2s into phi 1s. And the only way to do this is by sticking on a lambda 5 vertex. Remember, it was imaginary part of lambda 5 that we're trying to generate, okay? So we stick on a real part of lambda 5 vertex, that's fine. And this blob here is basically this with like all the extra legs connected together, all right? That makes a 6th loop, okay? So far, so good. And then we have to ask the question, if we complex conjugate this thing, are we going to get a cancellation? Now, on the surface, it would look like no, because if you look at this last loop here, it's attached at a different place from the J star, the complex conjugate diagram, okay? But that's the only difference. The only difference is basically the momentum flowing in this last sixth loop takes a different route through the rest of the diagram, okay? So does the imaginary part cancel? So now you have to like get out your thinking cap, right? Here's how our analysis went. We treated the sum, you can treat the sum of all of the 5 loop subdiagrams here that are proportional to J and not J star as a form factor. So this is just a function of momenta, a function of these 4 momenta, which has to have certain properties, right? And the properties that it has to have are, it has to be dimensionless, it turns out, because you can count the powers in the numerator and the powers in the denominator of all of the Feynman diagram pieces, and basically determine how many powers of momenta are in the numerator and the denominator. And the result is 0, or the net result is same in the numerator, same in the denominator, right? So it has to be dimensionless. This coefficient has to be dimensionless. It has to be analytic in momenta. It can't have any logs, right? And that's difficult to prove, but there's a way that it's proven in the systematic procedure of renormalization that's well known in the field, okay? And the combinations have to be Lorentz invariant. And you know that because like the whole thing has to satisfy special relativity. So the combinations of momenta have to be Lorentz invariant, okay? Now, doing the complex conjugation basically means you take this lambda 5 vertex and instead of attaching it here, you attach it over here on the other end after reversing the directions of the Higgs field flow, okay? And so if the form factor here has a piece which is anti-symmetric when you swap these momenta for those momenta, then the imaginary divergence will not cancel because you'll get a J star, but you'll also get a minus sign, okay? And one example of that is like if you have these momenta squared minus those momenta squared over some function of the momenta, okay, that would be anti-symmetric. But you can think about what happens when you start taking momenta to 0. This form factor has to be physically well defined at 0 momentum, right? Because it's a scattering process. If you take the Ka's to 0 first, you get something which is minus KB squared over basically some function of KB squared. If you take KB to 0 first, you get something which is Ka squared over some function of Ka squared, okay? Those two things are not the same. If you take the two limits, if you take the limits in one order versus the other order, you get a different result up to a minus sign. And so this anti-symmetric piece winds up, and the key is that it's dimensionless. The denominator is the same powers of K as the numerator. It lacks a well-defined 0 momentum limit. So terms like this have to be unphysical. Their coefficients must be 0 in any physical form factor. And that means that, yeah, when you add together these diagrams proportional to J and the complex conjugate diagrams proportional to J star, the imaginary part's going to cancel. Okay, so at 6 loops, also the imaginary part cancels. There's a way to understand this kind of more theoretically, which has to do with the fact that phi 2 goes to phi 2 is a Hermitian operator, so its coefficient has to be real, okay? I'm not really going to go into that. To screw this up so that we can preserve like a non-canceled imaginary part, I basically have to break this subdiagram structure. So that means connecting some other particle from the inside here to one of those external legs, right? And you can do that a few different ways. You can do that with an extra 4 Higgs coupling, or you can do it by exchanging a gauge boson, right? And because there are limited numbers of ways you can do that, you can actually predict what the parameter dependence is going to be of this imaginary part of lambda 5, of the divergence of the imaginary part of lambda 5. I'll explain what this differential equation is referring to in a second, but basically you need a lambda 5 real part. You need this imaginary part of this gigantic J thing, okay? And then you can involve, there's like 2 different Higgs couplings and then 2 different gauge boson couplings that could show up. And we don't know what B1 through B4 are because we didn't even calculate any diagrams. Those are just some numerical coefficients in front, right? And this factor here is because it's 7 loops. Now, what this differential equation is referring to is when you calculate the divergent, um, I have only like 2 more slides. When you calculate the divergent part of a Feynman diagram, the coefficient of that divergence also controls how the parameter runs with energy scale. So we have the couplings in the standard model and in particle physics in general are running couplings, meaning that the strength of the coupling depends on the energy scale at which the process is happening. Okay, this is super famously the case for the strong interactions, where at low momentum transfers, the strong interactions are very strong and you have bound states, hadrons. At high momentum transfer, the strong interactions get weaker and weaker, which is why you can calculate things accurately for the Large Hadron Collider. Right? That's called asymptotic freedom. In the high energy limit, the couplings become weaker and weaker for the strong interactions. And all couplings run like that. They just aren't as impressive as the strong interactions. And so if you make the assumption you have the running, you can set a boundary condition for this differential equation and run and see what you get. So if you set as the boundary condition, imaginary part of lambda 5 equals 0 at the Planck scale, which is where we usually put our ignorance, and run down to the electroweak scale, you get some ridiculously tiny number, 10 to the minus 22. So tiny, it has no conceivable phenomenologically detectable effect, right? Electron EDM, tiny effect. Mixing between the CP odd and CP even would be eigenstates of the Higgs fields, super, super tiny, right? And so you can continue to use the real 2 Higgs doublet model, but this all rests on like, why should this be 0 at the Planck scale? There's no reason. We don't know any reason why that would be the case. So probably better to accept that this is actually a potential new source of CP violation, which is somewhat small, so we haven't seen it yet, rather than, this is exactly real. All right, so let me conclude. There's a principle of quantum field theory that you can't truly preserve a symmetry in one part of the theory if it's violated in another part of the theory. And you can use the features of bits of quantum field theory, like the properties of the divergences of Feynman diagrams and overlapping approximate symmetries, to build up what are the required ingredients for such symmetry violation to transmit from one part of the theory to another, even when doing the full calculation is basically technologically impossible at this stage. And the interesting thing in this whole business is, in my opinion, that the Kabibo-Kobayashi-Maskawa structure of the quark mixing is very effective at hiding CP violation, at sequestering it, so that in this process, at least, it only leaks through in a divergent way at 7 loops, which is kind of like a ridiculously large number of loops, right? So I will stop there. I did want to flash this advertisement. I have written an open access guide to how to make your research group more inclusive for autistic trainees. It's only 6 pages. If you're interested, it's on the archive at this address, or this QR code just takes you to this address. All right, and I will finish there. And thank you very much.
Yeah, thank you very much. I'll just stop the thing.